this time we need to do the verification step. All right. Yeah, formula transformation. Yeah. Now I want to talk about several points in the problem solving. Yeah. In our thinking. Yeah. All right. In problem solving, formula transformation very important. All right. So you change the form of the formula, change it to make it more friendly. But when you make the change, you need to have some special goals you want to make. Yeah. So you need to have some big picture. Yeah. So what are you doing? Yeah. So your objectives. So where do you want to go? Those things you need to be very clear in your mind. Yeah. All right. So here, so let's talk about that problem solving. Yeah. We know. Yeah. So what we can use here, when we do the formula transformation, this recurrence relation, we can always use it, right? Because it's given. Yeah. Here, I want to say this recurrence formula does not rely on induction assumption. Yeah. Induction assumption, we make assumption, but we have to follow that assumption, yeah, because all the conditions in that assumption, we have to follow. We cannot violate any of the condition in that assumption statement. Yeah. But this recurrence relation, yeah, it does not rely on the induction assumption. That means we can always apply it, okay? Without any limit. Yeah. So that's the nice thing. Okay. All right. Now we need to look at the induction assumption this time. Yeah. So here, let me write that induction assumption. Recall that induction assumption. Because when you apply induction, we have to do it in a careful way. Yeah. So we cannot, extend our range. Our range, very strict. We cannot go outside the range. Yeah. We can only apply the formula inside that range. Yeah. So let me show you the meaning here. All right. Induction assumption, this formula, here I use this formula, yeah, only true for K is in this range. That's the induction assumption. Okay? Yeah. If we apply this formula, yeah, although here we replace M by K, okay, a K version. K version, okay? We apply the K version. When we apply that K version, if K falls into the given range, we can do it. If out of the given range, we cannot do it. Yeah, that's simple. All right. First, let's look at Fm. Can we replace Fm by this expression? Yes, because the first one, K equals N, right? This case, K equals N, and K equals N, it's in the range, right? So we can apply. It's legal. All right. Then for the second one, K equals N minus 1, also in the range, right? Then we can apply that formula. Okay? Yeah. All right. So based on the recurrence relation, F n sub m plus 1 equals this. It must be true. Because based on our induction assumption and the recurrence relation, F sub m plus 1 must equal to this one. Okay, all right. But the question, does f sub m plus 1 equals this expression? We don't know, right? We don't know. Yeah. Our goal, we want to, yeah, our objective, we want to show it is correct. Okay? So, that's the goal. Yeah. So we want to verify it's correct. Then we make it, right? Think about, if we verify it's correct, can we extend our range to m plus 1, covering m plus 1? Yeah, you can see it. Yeah, because, our induction hypothesis statement is valid for m plus 1. Yeah, so that's the nice thing. Yeah, all right. Then, but these two expressions are the same. At this point, we cannot see it, right? Still, long way to go. Yeah. So our next question, we only need to verify this identity. Yeah. Left-hand side, right-hand side, we need to verify this identity. Okay, all right. So we move to our next step. The question is how to verify these two formulas are exactly the same. The next question, all right. Yeah. So here still, in our problem solving, yeah, we know the structure is very important in our problem solving. The structure. The formula, you have some special structure, right? Exponential function, reciprocal function, the root something, structure. Yeah. All right. Here, when we compare two formulas, left-hand side, right-hand side, two different formulas. Yeah. When we compare them, we want to compare the terms with similar structures. The terms with similar structures, there, they should have some intrinsic relationship, right? Yeah. 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 So that's some understanding. Yeah. Some general understanding point. Yeah. All right. Then, so let's rewrite. Here, we rewrite this formula. When we rewrite this formula, we take that 1 over root 5 out. Then, inside the big parenthesis, there are 4 terms. In these 4 terms, let us put the monomial terms together. Yeah? Monomial terms, they have the same structure, right? Yeah. Then, reciprocal of monomial, they have the similar structure, right? So, when we consider the structure, here basically we have 2 different structures. The first, monomial structure. The second, reciprocal of monomial structure. All right. Here, if you look at, because this 1 over root 5, the same. So we can ignore, right? Yeah. Same, both sides, the same. Same constant. Yeah. Then we only need to compare the part inside big parentheses. Yeah. But inside parentheses, there is also monomial part and reciprocal of monomial part. Right? Can you imagine we should, if we want to make some reasonable guess, can we guess that the monomial part of the first expression should be equal to the monomial part of the second expression? The reciprocal part should be the same as reciprocal part? Yeah? Because the structure, structures are right. Yeah. We align them according to the structures. Yeah. Yeah. In that way, we split them into 2 parts. Okay, all right. Yeah. The monomial part, yeah. So the monomial part, one side, left-hand side, yeah, we put it here. The right-hand side, these 2 monomial terms, we put it here. Okay, all right. The question. Can you see, if you use your eyes to, examine, can you see this equality should be true? Yeah, all right. Yeah, one more step. Yeah, if you cannot see immediately, yeah, let us, yeah, all right. So that's one. The second one is the reciprocal of monomial terms. Yeah, yeah. should be like that. Okay. All right. Yeah. But for the first one, we start with, this is our second property of golden ratio, right? Second property. If you multiply the same expression, phi to the negative n minus 1, both sides, do you get that? Yeah. 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 Just one simple multiplication. You can make it. All right. Then, so we make the first one, but the second equality verification, yeah, looks a little more complicated to verify it. Yeah. But to do it, yeah, so now we apply. Yeah. So now our goal, this is our current goal. Yeah. All right. Now we want to use some backward thinking. Yeah. All right. Backward thinking, yeah. Let's do some deductions. If this expression is true, what can we get? Okay? Yeah. Because although it is our goal, so this actually is our goal. Yeah. But we do deductions starting from our goal formula. Okay? Yeah. Going backward. Yeah. If that formula is correct, then we do transformations. Going back. Okay? All right. The transformation, the first one we want to do, remove the common denominator. Common denominator. This is common denominator. So we multiply common denominator. We can eliminate all the denominators. Yeah. All right. After we remove the common denominator, yeah, so we have this expression. But this expression, you have -1 to certain power, multiply some terms, and you see this negative, these, -1 form to some exponent. The form, it looks like noise, right? Noise to our main body of the formula. So we may like to do something, denoise, remove the noise. Yeah, that because that's the distraction factor. We want to remove the distraction factor. Okay, all right. So we do another transformation. We multiply both sides by this special -1 to the n minus 1 power. Yeah, because in that way we can simplify to get rid of all the -1 to certain power form. Yeah, we don't need that. We want to denoise it. We want to remove the distraction factor. Yeah. After that, after simplification, you get the left-hand side just the 1, right-hand side, yeah, because after this multiplication, it's positive. So the coefficient of phi squared positive. The coefficient of phi negative. Yeah, because the exponent is an odd number you're adding together. So it's a negative. And this matches the first property of golden ratio, right? 1 equals phi squared minus phi. That's exactly our first property of the golden ratio. We know it's correct. Yeah. If it is correct, yeah, because our transformation always two-directional, right? Both directions. We can, do these algebraic transformations both ways. Yeah, always both ways. Can we going forward? Yeah, yeah. Because this is true. We just going forward, right, along the path. Yeah. So we get to our destination. Yeah. After these two steps, our conclusion. Yeah, yeah. So this formula is correct for all positive integer n. Yeah. Here, you can see I spent a lot of time to talk about mathematical induction. Yeah. So you need to learn, understand this powerful method from problem-solving point of view. Yeah. Yeah. later, because sometimes people observe some special phenomenon. Yeah. You know, why this special phenomenon always occurs? Yeah. Sometimes people can see it. Oh, so then people write down, oh, this special thing always happens. Yeah. All right. But after that, you may want to show, yeah, so that special property always true. Yeah, you need to prove it. Yeah. In that situation, yeah, this mathematical induction, you need to connect to this mathematical induction. Okay. Yeah. All right. Yeah. So that's our first topic of this part D. Yeah. Then we need to move to the second topic. Yeah. All right. D.3, linear recurrence relations. Yeah. Actually, in this part, we want to solve second order. Not first order we did before. Yeah. So solve second order linear recurrence relation. First order, we did in that Tower of Hanoi problem. We did it. Yeah. So you have some background. So that's the background. How to solve the recurrence relation, the Tower of Hanoi problem. So let me write that first order recurrence relation. Sorry. Yeah. Plus 1. Okay? Yeah. All right. C of 1 equals 1. Yeah. That's the first order. Okay? Yeah. First order, yeah. Yeah. Let me recall some useful properties in our solutions for this first order recurrence rate. The first thing, remember, this term is special. This term, yeah. This term, we modify the problem, we remove it, right? In our modification version, we remove that constant term. Okay, all right. After we solve it, then we make connection because there is a gap. Okay, non-constant version, constant version, there is a gap. So we make that connection. The connection is we could use a D function that equals C function plus 1. Okay, when we introduce a new D function, we can connect these two versions. Yeah. But another problem, when we ignore this constant term, the solution of this one is power of 2, right? Power of 2. If we ignore this constant term, the solution has this form. All right. So that's what we had before. All right. Yeah. So let's put it aside. Okay? Put it aside. Because later we need to make connection. Yeah. Yeah. Because in our problem solving, what we are basically doing here in problem solving, connecting the dots. Yeah. There are many dots we need to connect. Okay, all right, many dots. This is one of the dots. Okay, yeah. So this information here, one of the dots. We need to make connections. Okay, yeah. So if you have a lot of experience, a lot of knowledge, yeah, so you know how to connect the dots. Okay, yeah. Yeah. Here, let me show you how to do this connecting the dots thing. Yeah. All right. Yeah. First, the formal name of this equation. You can see the long name. Second order, yeah, I already explained second order. Linear, homogeneous. So linear. Can you see this is the linear equation? Yeah. Because there is no nonlinear term. Here, I can try to create some linear term. Okay, for example, f squared. That's nonlinear term, right? You have a square. Okay. Another is if we have a product minus 1 times the product of two functions. That's nonlinear term. Okay? Yeah, nonlinear term. Here you can see, yeah. So the linear term, you can only use constant multiply and constant multiplication. Then it's a linear term. Yeah. All right. So linear. Homogeneous. Homogeneous means the constant term is 0. Here, 0 constant, right? No constant. No plus 1. Yeah. If the constant term is 0, we call it homogeneous. All right. Recurrence. You know recurrence. Recurrence relation with constant coefficient. Yeah. The constant 1 here. Okay. Constant 1, constant 1. Yeah. It's not constant. So non-constant, you can see if I make this Fn equals n times Fn minus 1 plus, n minus 1 times, yeah, then it's not a constant coefficient. Okay, yeah. So here you can see our equation. We use this long name to describe it. Yeah. All right. Then the general such equation, yeah, because what we have here is a special equation. But here remember, I want to find a systematic solution, not a special solution. This systematic solution covers, the general problem. Yeah, not just this Fibonacci, this recurrence relation. Yeah, any recurrence relation in this form, it can cover. So now we want to find that solution. Yeah, yeah. So b not equal to 0. Yeah. Because if b equals 0, what would happen? If b equals 0.
That means it doesn't exist.
Well, not doesn't exist. It becomes a first order recurrence relation. First order, we studied before. Yeah, so we don't worry about first order. Yeah. So that's why we want to assume b it must be non-zero. So
I was thinking in the case that the Fibonacci number is actually 2, then 0 minus 0 would just be a 0.
Yeah.
Which it just means that it's 1.
Yeah, yeah, right.
Or the Fibonacci number. So,
Yes.
Yeah, go ahead.
Yeah. Just like quadratic equation, your leading coefficient becomes 0.
Yeah.
Then you cannot apply quadratic formula, right? Yeah. So you go back to the linear equation. Yeah. Similar. Yeah. All right. So here, our Fibonacci, just special case, A, B both equal to 1. Yeah. All right. Solving. Yeah. So here, because here you can see our Fibonacci number problem is so simple. Yeah. We want to use that example to illustrate the problem-solving process here. Yeah. Because that same process can be applied to the general recurrence, second-order recurrence relation problem. Yeah. So here we use the Fibonacci number example. Yeah. All right. Yeah, so now let's work on this problem. Yeah. All right. Actually, this topic, you can, this whole topic, solving second-order recurrence relation, you can find it in your discrete math. Yeah. So there is one section talking about that. Yeah. But here, I want to use the, problem solving. So that framework, yeah, problem solving framework, to, try to, show you how to connect the dots. Yeah, yeah, yeah. All right. Let's take a special view here. All right. Yeah, this step is important. Yeah. Remember, we want to get an insight. Yeah. So when we work on a problem, we want to get insight. Yeah. Here, we want to take a special view to see some special point, very important. Yeah. All right. Here. All right. because this sequence here, this sequence. So here we consider sequence. So here, we look at the Fibonacci numbers. All the Fibonacci numbers, we look at all these numbers as a special sequence. All right, a sequence. Yeah. All right. Then we think about, for this special sequence, how do we describe this special? Can we have a special way to describe the sequence? Yeah. All right. So here, let me point out another important idea in problem solving. Yeah. Another idea in problem solving. Yeah. So, yeah. Very common. Yeah. That step is called modeling. Modeling. Okay. Yeah. Here, mathematical modeling. Yeah. When you solve real-world applications, because the phenomenon is hard to describe. Okay? There is some phenomenon, special phenomenon. Yeah. But how do you describe that phenomenon using some formulas? Yeah. So usually, for engineering people, yeah, because solving real-world problems, engineering people, they need to solve a lot of real-world problems. Okay. One important step, they need to make mathematical model to describe the real-world problem. Yeah. So what kind of mathematical model? Physical laws. Yeah. So they use physical laws as the mathematical model. Okay. The Newton's laws. Okay. So this problem fit in the Newton's laws. So they use Newton's laws as the model, okay, mathematical model to describe this problem. Then another different law, okay? Yeah. So for different field, yeah, electric circuits in a different field, then you use different laws, okay? Yeah. So many different physical laws they can apply to solve real-world problems. Yeah. So that's the typical situation. Yeah. Here, yeah, we have the similar situation, although not that, physical laws. Here we do not use physical laws. Yeah. But here, what do we need to do? Yeah. We need to use the concept mathematical model. Yeah. So the mathematical model, what's the mathematical model? Certain formulas. The formulas with certain structures as the mathematical model. Okay? Here, yeah. What special formulas do you want to use to describe the sequence here? Yeah. At this point, you have no idea, right? You need some inspiration, right? Yeah. Here, let me point out one special knowledge point as the inspiration. Yeah. The Tower of Hanoi problem. In the previous slide, Tower of Hanoi problem. Okay, all right. So let's make that connection. Here, we write the recurrence relation, first order recurrence relation. Here, I write this is the homogeneous form. I drop that constant term, then it becomes homogeneous form, right? Yeah. Because here we are working on the homogeneous version. So we do not need to use the constant term. Yeah. For the homogeneous version, what's the solution? The solution to, n minus 1, okay? Yeah, so are similar. Yeah, similar, yeah, n minus 1. When you see this form, what kind of inspiration can you get? Yeah. As I said, the special form structure, we use it as the model. What kind of model do you want to use? Inspiration, after you see. Yeah, because this problem, although different from that one, but it's just a lower order version, right? here we have second order version, but we know the structure of the first order solution. The structure, all right, so let me go give you another hint information. Yeah. The solution form of the first order recurrence relation is a power function, right? Yeah, it's a power function. Yeah. Here the question. Do you feel the solution for the second order recurrence should also be a power function?
It could be. If it's two functions that taken separately, then they are both power functions.
Right.
So it could be another.
Could be. Yeah. So here, what I mean, the inspiration. Yeah. Because we know, as a whole, recurrence relation equations, yeah, all those equations, they should have some similarity, right? Yeah, they should share some first order recurrence relations, second order recurrence relations. At least they should share some similarities internally, right? Yeah, inside. Yeah. But is that kind of inside similarity could be their solutions could take the same power function form?
I think so.
Yeah. So we can, at least we can try, right?
Yeah.
At least, so that's why I said after we got inspiration. Yeah, because this is what we have seen. Okay. Yeah. That's 100% true. Yeah. Yeah, we prove it. Yeah. So then next thing is, because in problem solving, another thing we need to do. We need to, many times, we need to make a lot of very brave imaginations. Yeah. Yeah. So if you worry about this, worry about that, worry too much, so you cannot go forward. Yeah. So when we try something new, we have to make some, very brave imaginations. Here we need, because here, because you have no reason to assume the solution form of the second order recurrence relation also take the power form, right? Yeah, no reason to assume. But because we see the solution in the first order, there we just make some brave assumption here, right? So our next thing is, so this thing we need to do frequently in problem solving. Yeah, many times. Yeah, we guess the structure is a special power function. Yeah. This power function here, another view of this power function, that's what I said, a mathematical model. So here we use this as the model. Okay? This is just like the Newton's law. Okay? Newton's law, you need to fit in the Newton's law, right? Here we don't have the Newton's law, but we have this power function, mathematical model. So we need to fit our solution in this model and see if it works well. Yeah? So here you can see the reason I talk about all those things, because problem solving basically is about how do you understand the problem. Here, all these things I talk about, that's the way we understand the problems. Yeah. All right, so now, because this step is very critical. This step is critical. Yeah. All right, so this we call the geometric sequence. Then, now, because we want to see if this model can be used to solve the second order recurrence relation well. Okay? All right? So let's try it. Okay? Nothing to lose. Yeah. But this little t is unknown here. Yeah. Because it's unknown. Yeah. We can make our decision. Yeah. We can choose appropriate little t to get a solution. Yeah. Yeah. We have freedom. We have freedom to choose little t. Yeah. All right. Yeah. So now let's plug in. Yeah. So because if we make a sub k equals this t power function, t to the k function. Then, we can write a sub k minus 1, a sub k minus 2 also as this t power function, right? Yeah. This equation, can we solve it easily? This equation, yeah. After simple, yeah, here, because we can do cancellation. After cancellation, we get this equation. Do you see this equation familiar? Quite familiar? With
property for what's it called? The golden ratio?
yes,
Yeah.
exactly. Golden ratio property. Okay, that's exactly the golden ratio property. Then we can find two solutions. Yeah. T1 and T2. Two solutions. Then what's next?
We verify the
Yeah. Yeah, we verify. Yeah. Okay. But the first question I want to here, T2 solution is a negative number. How do you feel about this negative number?
If it's a ratio, then you can have a negative number.
Yeah. Yeah. If its original meaning is a ratio, then we cannot take this negative number. But here, this t, does it mean the ratio of something? This t here?
No, it means it's a part of a sequence.
Yes. This is in our model, it's the base of the power function. It has nothing to do with ratio, right? If it has nothing to do with the ratio, we have no reason to drop it, right?
Yeah.
So we should keep it. Yeah. So here, don't drop it. If you drop it, you drop some valuable information in your solution. Yeah. All right. So now our conclusion is we get two different solutions. The first solution, we use a T1 sequence. The first solution, we use a T2 sequence. Two completely different sequence solutions. How about that? Yeah. All right. Yeah. Next thing. Yeah. Now, two special solutions. All right. Yeah. So, and these two special solutions, if you plug into our, recurrence relation, both should be true, right? Both should be true. Yeah. No problem, because we derive these two solutions from there. Okay. Yeah. So these two must be true. Yeah. All right. Then the question. At this point, we find two different solutions, but they are non-integer solutions, right? Yeah. Non-integer solutions. Our Fibonacci numbers, they are integer solutions. So still far away. The gap is still pretty big. Yeah. The gap is so big. Yeah. So we need to bridge that gap, right? Non-integer solution and integer solution, that gap, we need to bridge it. Okay. Yeah. The question, how to bridge that gap? That step. All right? Yeah. Yeah. So here, there is another important step we need to do here at this point. Yeah. That is, here we have two special solutions, right? Yeah. Two special solutions. All right. And you want to get general solutions, right? Yeah. Because two special solutions, it is very limited. The things you can do, very limited. If you have more general solutions, then you can imagine your general solution should contain the Fibonacci numbers, right? Yeah. Because these two special solutions, too special. So they have nothing to do with Fibonacci numbers, right? But if you have a chance to get general solutions, then, yeah, so that big umbrella should cover that Fibonacci numbers. Yeah. So your next objective should be, you want to go from these two special solutions to a general solution. Yeah. More general solutions. Yeah. The question, how to get there? Yeah. So here, the idea, also very simple. Yeah. We use some special formula to write a general solution based on the two special solutions. One special formula. We can use formulas. Yeah. Here are the questions. How do you apply some special mathematical formula that provides some reasonable way to combine two special solutions? The combine way, you have millions of different ways to combine, right? You have millions of ways to combine two mathematical objects. But here, you want to choose a reasonable way to combine two solutions. Reasonable way. Yeah. All right. Here, one more step. I want to give you that information. Yeah. So, yeah. Here we can, forget about initial condition. Yeah. We will fix initial condition later. Okay. All right. So the question. Yeah. Yeah. All right. So we do not at this point we do not look at the initial condition. Yeah. We just want to use these two special solutions to get a new solution. Yeah. And we add initial condition later. Yeah. So we get a new solution formula first. Then we, try to, resolve that initial condition part. Yeah. All right. So here, we need another special way to do the combination. All right. So here, let me describe the special way. Yeah. All right. That special way, yeah. All right. We call the linear combination of two variables. Linear combination. Yeah. Here, I want to talk about a basic concept called the linear combination concept. What's that linear combination concept? Okay, all right. Here, what is the meaning of linear combination of two variables, x variable and a y variable? Then we want to use a formula to represent linear combination of x and y. Yeah. That's ax plus b. Capital A, capital A, two constant numbers. So you have freedom to choose capital A, capital B. For any constant A, constant B, if you write this form, A times X plus B times Y, we call it a linear combination. Yeah. Linear combination form has a special property. Yeah. Special property. All right. So we call the linearity property. Yeah. So the property we call linearity property. Sorry. Linearity property. What's that linearity property? All right. That is, if your x satisfies the equation, one linear equation, y satisfies the same linear equation, then your linear combination also satisfies that linear equation. That's the property. Okay? Linearity. Yeah. Inherent. Yeah. So here, our x, that's our T1 solution. Okay? Our T1 solution satisfies this original recurrence relation. Our T2 solution also satisfies original equation. Then our linear combination A T1 solution plus B T2 solution, linear combination also satisfies the original linear recurrence relation. That's the linearity property. Okay? Yeah? Because our recurrence relation is a linear recurrence relation. Linear recurrence relation should have the linearity property. Now we use the linearity property. Okay? The linear combination takes advantage of linearity property. Yeah. Now we use this property. All right? Yeah. Linearity property here. Yeah. All right. Any linear combination of two solutions is also a solution. That's the linearity property. Okay? All right? So the new form of the solution, we use some constant capital A, capital B to be determined. Yeah. Yeah. So there are free parameters. Yeah. So capital A times the first sequence solution, plus B times second sequence solution. Okay? Then adding together linear combination, this whole thing with two freedoms, right? Yeah. Freedoms means we have more rooms to manipulate the formula, right? Yeah, it's not fixed formula. So we have freedom to, to change things. Yeah. All right. And this new form satisfies the original recurrence relation. You can see that, right? You can see that easily. Yeah. 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 All right. Yeah. Then the next thing is, because we have these two freedom parameters, can we use these two freedom parameters to help us resolve the initial condition? Yeah. So that's the place we use these two freedoms. Yeah. We have room. Yeah. So we can, adapt these two parameters to match the initial conditions. Yeah. So that makes sense. Yeah. All right. Yeah. So then our next step, we just, determine the coefficients, capital A, capital B, such that the initial condition is satisfied. Initial condition, yeah, F0, A0, A0, F0, A0, yeah, F0 should be 0, right? Yeah, Fibonacci F0 should be 0. Yeah. Then we plug in N to be 0, yeah, it should be 0 value. 0 means B equals negative A. Yeah. All right, so we can eliminate B, replace B by negative A. All right. Then for N equals 1, yeah, A1 is F1, right? F1 equals 1. Yeah. Then we plug in, but B is negative A. Can we replace B by negative A? B, negative A. Yeah. So we can eliminate the B. We don't want to see B. Yeah. So then this number equals 1, but if we replace B by negative A, we can do simplification. We factor that A out. Then inside the first parenthesis minus the second parenthesis, yeah. After simplification, we get A times root 5 equals 1. Okay? Yeah. So you can find A value capital 1 over 5, root 5, 1 over root 5. And the B equals negative 1 over root 5. Yeah. Can you go back to the original formula? Because you get an A and a B, right? You replace A by 1 over root 5, and you also replace B by 1 over root 5. Yeah? If we use the golden ratio expression, yeah. That one reciprocal of golden ratio, but a negative reciprocal, right? Negative reciprocal. Yeah. Yeah. So this is a negative reciprocal golden ratio. Yeah. So then, yeah, you replace A by root 5, B negative root 5, so you get this expression. Yeah. That's the one. That's the right formula. But this way we discover it, right? Yeah. So it's not a verification way. So it's the discovery way. Yeah. But this discovery way, here you can see a lot of problem thinking points. Yeah. We need to, every step we make some progress, we need to do something right. Then you can make it. Yeah. All right. Here, let me recall. Yeah. Or not recall. Here, let me do some summary. Yeah. So, because we find a solution. Yeah. So we solve this problem. Yeah. And later, for any second order linear homogeneous recurrence relation, you can use this way. You can use this way. Yeah. Here, another comments. Yeah, comment. Some students know that. Yeah, based on my grading. Yeah, I noticed many students know that when solve second order recurrence relation, people find the characteristic equation first. Solve characteristic equation first. Yeah, Many people know that concept. Here, what's the characteristic equation? So you start from the original equation. Then you write its corresponding characteristic equation. Yeah. This term, yeah, you use x squared. Yeah. Because its subscript is 2 more than the lowest one. Yeah. So that difference number you use here. Okay. Then this one you use x plus 1. This we call the characteristic equation. Character. Yeah, characteristic equation. All right. Yeah. Yeah. So then, how do you find solutions? So you use the linear combination A, so that power function plus B, second root power function. Then you use the initial conditions. You can figure out, calculate capital A, capital B. Yeah. So that's the, general way. Yeah. All right. Yeah. But here I want to recall several points useful in problem solving. Yeah. The first, mathematical modeling. Yeah. So when you solve a problem, yeah, because if the data you have, you want to control the data, right? The data given Fibonacci numbers, that's the data you have. If the data you do not control its structure, it is hard to handle, right? Yeah. So we want to, use the right structure to describe our given data. Yeah. So that right structure, that's our model, our mathematical model. So we need to choose the appropriate mathematical model to describe our data. So that's one point, valuable point. Yeah. Second point, for the similar type of questions, so here the first order recurrence relation, second order recurrence, they should share something common, right? Yeah. So here, based on our imagination, their solution should share the same structure, power function structure. Yeah. Then, because we can get a solution from the first order recurrence relation easily, it's a power function. Then, naturally, we extend it to the structure of the second order recurrence relation. That's another point. Okay? Yeah? Inspiration, yeah? But this inspiration, so you need to, so your understanding should get there. Okay? Yeah. After you see this, it inspires you to do something special. Okay? Yeah. So if you worry too much, you do not want to go forward. After you see this power solution form, you'll worry too much. Because you're not 100% sure if it's correct for the second, you do not want to try. Then you can never get it, right? So here, we want to try. Okay? So when we get something interesting, we want to try it. Yeah. So that's the second point. Okay? All right. The third point, that's linear combination concept. When you have a linear equation and you have two solutions, to get a general solution, you should consider the linear combination way to combine the known information from the two special solutions to form the general form of the solution. Yeah. That's the linear combination concept, method. Yeah. Simple. Yeah. But if you do not know it, it may not be easy, right? How can you, how suddenly you know you should do that, right? There is no reason to do that, right? Yeah. Yeah. But after So that's why, although this question pretty mathematical, right? Yeah, because I know many computer science students, they hate math. They hate math, yeah. So, yeah, because they ask me, why you talk so much about math, right? Yeah. But here we understand in this way, the reason, although math useful in algorithm, that's one thing, but the second thing is because I want to make some points in problem solving. Yeah. The idea, many ideas we use in math problem solving, computer science problem solving, similar, right? Yeah. Because many strategies, very general. Very general. Yeah. So here, the reason we use math as examples, because it's very easy to get math examples, right? Yeah. Because it's pretty hard to get engineering examples, computer science examples, much harder to get those examples, right? Because you need to make up a lot of information related to the real world applications. For math, we don't need to connect to the real world problems. Yeah. All right. So that's another thing. Yeah, important. Yeah. For this one, I think these 3 points. After you learn this example, if you can understand these 3 things, then I think you. Oh yeah, I get to the end. Yeah. So yeah. So then, I think it could be very helpful in your future problem solving. Yeah. Yeah. All right. Yeah. All right. Let me stop right here. Yeah. So we finished module 3 today. Yeah. Now we can focus on our midterm exam. Okay. Yeah. So for the remaining of the semesters, you should focus on midterm exam. Now I'm doing the grading of homework assignment number 1. So I expect I will complete it sometime tomorrow. Yeah. So before my Wednesday's class, I will complete the grading. Yeah. Then I will send you back my graded papers back through the Canvas. So you can download my graded paper.